Let us prove the following proposition. For any set A, B, and C, the following statement is true. A union B intersection with C equal to the intersection of two sets. The first one is A union B, second one is A union C. Okay. So to prove this statement, we need to show, to prove this proposition, in fact, we need to show that the left hand side set is a subset of the right hand side set and the other way around. So let's recall this. To prove set A equal to set B, this is the way we usually do. We show that A is a subset of B and B is a subset of A. That's the ways we do. So we need to prove two containments. The first one and the other way around. So let's do that. So we first show that this direction. We first prove that left hand side is a subset of the right hand side. So how do we show a set is a subset of another one? Pick an element here, say X in here. We want to show X is an element of the right hand side, right? Let X be an element of A union B intersects C. We need to show that X is an element of the right hand side set. Okay, now let's start from the hypothesis. What do we have now? X is an element of A union with this intersection B intersects C. Okay. By definition of the union, X must in A or X in B intersects C. What? So A union big B. So X in A or X in big B. What? X in A or X in the other set. So let's do two cases. We consider case by case. Suppose X in A, what happened? X is in A. Then X must be an element A union B. Union B by definition of the union. What? A union B. We did actually, let's just note here that we did prove this. We proved that A is a subset of A union B, if you remember that. Okay. And similarly we have, and we also have X is an element of A union with C. Right. So this is the first case. So we have X is an element of A union B and X is an element of A union C. Therefore, X must be in the intersection of these two sets. In the intersection A union B intersect with the other one. Okay. So what is this? This is exactly what we need to show, right? It's the same. So we did prove this part. X is an element of A union B intersects with A union C. So therefore we prove the first part. Therefore, for this case, A must be, therefore X will go from here, we reach there. Therefore, this one is a subset of this one. What about the other case? Now, second case, X in here, B. Suppose X is in B intersects C. By definition of the intersection, X must be an element of B and X must be an element of C. Okay, so X is an element of B. By definition of union, X must be an element of B union A, right? X is an element of C. X must be an element of C union with something. Something here has happened to be A. So we have this. Then X is an element of B union A and X is an element of C union A. Right? Therefore, X must be an element of the intersection of these two sets, which is this one. So in two cases, the first case and the second case, we both have X is an element of the intersection of A union B and A union C, which is what we need to show. Therefore, we prove the first containment. And so we showed it. That. Okay, so the first containment is done. Let's do the other way around. Let's prove the second containment. So here's the first part. Now we do the second part. Now we prove the opposite containment. Which is this one. Let me write like this. The right hand side set is a subset of the left hand side set. Right? So how we do that? We pick an arbitrary element in this set. We want to show it is also an element in the other one. Let X be an element of this set. We want to show X is an element in here. Right? Show that an element of this one. So for this part, we need to show X is in A or X is in B intersects C, right? By definition of the union. So to make it easier, one way we can do is consider case by case. Case 1. Suppose X in A. In case 2, suppose X is not in A. Okay. So if X is in A, we want to show this. If X is not in A, we want to show this. Right. So that's the only case we can possibly have. X in A or X not in A. Right. So let's do the first case. Suppose X in A, then what happened? X in A, then by definition of union, X must be an element of A union with something, whatever it is, and in this case, ECB intersects C, right? So we did show this part. Okay, so the first case is easy. The second case, if X not in A, then what happens? X is not in A, and so let's start from the hypothesis. We have X in this intersection. Since X is in this intersection, by definition we have X is in the first set, and because this is the intersection, right, and X is in the second set. So it makes sense, right? Okay, so now we have that. For the first things, we have X is, since X is in A union B, this case, and we are in the big case that X is not in A, and X is not an element of A. Therefore, by definition of the union, so A union B, A union B, X not in A, so X is not there, but X in A union B is the whole thing here, right? Therefore, X must be somewhere there, right? Just picture, we have X must be an element of B. I hope this is clear enough. X in A union B, but not X is not in A. Therefore, X must be in B. Right? Otherwise, it couldn't be inside the union. Okay, similarly, you can do the same argument. We can say that since X is in A union C, and in our case X not in A, we have X must be an element of C. So we have X in B and X in C, right? This is our N. So now we have that X in B and X is an element of C. Therefore, then X must be in the intersection of B and C, right? By definition of the intersection. Okay, what happened now? X is in the intersection of B intersects C. So that means that X must be in the union of B intersects C with whatever we like, and in this case we choose to union with A. Therefore, X is in the union of B intersects C with whatever we not like, and we like A in this case. So that is exactly the same as what we want to show. What is contained in this set. Therefore, in any case, X in A or X not in A, we both have X in A union B intersects C, or X in A union B intersects C, right? So we did show this. what we need to show. Right. Therefore, we have this container. We prove it. And we prove two containment, the first one and the second one, which means we prove the equality. Two sets are equal. Right. We prove two sets are equal. Thus we are done. So that is a way to prove this proposition.